In this section, we're going to specifically try to reduce second order differential equations down to first order differential equations, hence the name reduction of order. So we'll start with something like a sub n of x. Actually, I shouldn't say a sub n, when in fact it's just going to be a sub 2 of x y double prime plus a sub 1 of x y prime plus a sub 0 of x times y equals 0. So we're going to be sticking with homogeneous equations, but they will be of second order. Well, the first thing that you'll do, we'll assume that this a sub 2 is not equal to 0. So we'll say a sub 2 of x does not equal 0. So, well, the first thing we're going to do is divide by that. And if we divide everything by a sub 2, we get an equation like this. And then, of course, these can be whatever rational functions or whatever they may happen to be. They can be more complicated than that. We are going to look at equations like this. So it'll just be easier to do the computations with it in this format than this crazy format up here. So these are the types of equations that we'll be working with. The very first thing you're going to do is divide whatever's in front of the y double prime out. Okay, let's suppose y equals c1 y1 plus c2 y2 is a solution to this equation. So if we assume that that is a solution, and we happen to know one of the solutions, say we happen to know y1. Well, then this method will show, the method we're going to use here will show us how to figure out the y2. One thing that you should know, since y1 and y2 are linearly independent, what I mean by that, linearly independent, is if it so happens that c1 y1 plus c2 y2 equals 0, this implies that both c1 and c2 are equal to 0. So you can't come up with constants that add up to be equal to 0 with this y1 and y2. As a consequence of that, y1 over y2 can't be constant. The reason why it can't, if it were, suppose if you had a situation like y1 over y2 were equal to some constant, the first thing you would do is multiply through by the y2, and you would get c y2. And then when I take it to one side, I would have 1 times c1 plus negative c. Did I say c1? I meant y1 here. 1 times y1 plus negative c times y2 would equal 0. Well, the 1's not 0. Well, then that would mean the constant would have to be 0, but then you would have that y1 would be 0, everything would fall apart. So this is what we must have. This stuff down here cannot happen. All right, So it can't be constant. So let u of x equal, I'm going to actually turn that upside down, y2 over y1. y2 is the guy we're trying to find. y1 is already known. Let's multiply through by y1, and we'll get u y1 equals y2. And we're going to be doing a bunch of stuff with this, like taking second derivatives and all that kind of stuff. Watch what happens here when we do that. I'm going to take this, plug it back into our differential equation, and show you how it works. And then we'll do a few examples to illustrate that. So W2 will equal all that stuff, or Y2 will equal all that stuff. So what I'm going to do is let's just do it. Y2 equals U Y1, Y2 prime equals U prime Y1 plus U Y1 prime, and then y2 double prime. Since I'm going to have to plug all these things into the differential equation, I have to use a product rule on these pieces and a product rule on these pieces. So starting with the product rule for u prime y1, we'll have u prime prime y1 plus u prime y1 prime. That takes care of the product rule for those. And then over on the other piece, we'll have u prime y1 prime plus u y1 double prime. I'll simplify that just a little bit. U double prime y1 plus 2u prime y1 prime plus u y1 double prime. We're going to plug that into our differential equation. So our differential equation is y double prime plus p of x y prime plus q of x y is equal to 0. All right, and I know already that y1 is a solution. That means if I had a 1 in each of these spots, that would be true. Let's plug these things in. So we're going to try and plug in the y2. So y2 double prime plus p of x y1 prime plus q of x y equals, all right, so our y2 double prime we have done here. I'll get u double prime y1 plus 2u prime y1 prime plus u y1 double prime plus p of x times, and now let's plug in the first derivative. I'll get u prime y1 plus u y1 prime, and then finally plus q of x times u y1. All right, let's do some work on these things. Starting, first of all, what I'm going to do, since I already know that y1 is a solution, I'm going to strip out the y1 primes, double primes, and everything else out. So I'm going to have u double prime y1 plus 2u prime y1 prime plus p of x u prime y1. I pulled this term out of there. I took the first two terms from the first one. Now what I'm going to do is plus, I'm going to grab the terms that I haven't used yet. I have u y1 double prime, u y1 double prime, plus p of x u y1 prime, plus q of x u y1. And I'll do one more step. I still have this first stuff. That's not going away. I have u double prime y1. I am going to combine, I'm going to factor out a u prime from the second two terms, plus, so I'll have 2 y1 prime plus p of x y1 times u prime. And then I'm going to have plus at the bottom. I can factor a u from absolutely every term. And what I'll be left with is y1 double prime plus p of x y1 prime plus q of x y1. Now let me write it one more time. I have u double prime y1. I'm going to replace this stuff in here. Actually, no, let me leave it there for just a minute. Plus 2y1 prime plus p of x y times u prime plus u. All this stuff in parentheses equals 0 since y1 is a solution. So if this were equal to 0, here's what we would end up with. Keep in mind, 0 because y1 was assumed to be a solution. All right, now let's go ahead and here's what we're going to have left. I'm going to put my y1 in front of there. And what was left is this all equals 0. Now I'm going to divide by y1. And then just for the purposes of this illustration, I'm going to rename all of this. This is a function of x. So I'm just going to simply rename all that stuff as r of x. And all I'm getting at is now we have a type of problem that we can easily solve. You will let w equal u prime. With that in mind then, w prime will be u double prime, and we'll get w prime plus r of x w equals 0. And now this is really simple. You can use an integrating factor, which is e to the integral of r of x. I specifically didn't try to figure that out. We'll do that on a problem per problem basis. But once it's in this format, you can go and get w. Once you get w, you'll go back and integrate to get u. And then once you know u, you'll be able to get your y2. So those are the steps we'll go through. A lot of steps for these problems. Hopefully you're starting to see that this course can be quite computational. For our first example, solve y double prime minus 25y equals 0, given that y1 equals e to the 5x is a solution. So what I mentioned before then, you would want to let u equal y2 divided by y1, or y2 equals u y1. I'm going to not do, you're going to find that having a sub 2 throughout all these computations will be annoying. So I'm just going to get rid of it and plug it in as just y. We'll start with y will equal u times y1. So whatever u is, I don't know what it is, but it will be u times e to the 5x. Y prime will equal u prime e to the 5x plus the derivative of e to the 5x is 5e to the 5x. So we'll get 5u e to the 5x. And then finally, y double prime will equal u double prime e to the 5x plus 5u prime e to the 5x plus another 5u prime e to the 5x. And then finally, the derivative of e to the 5x will give us 25u e to the 5x. And just as I did with these things, I can simplify just a little bit. by combining the middle two terms. All right, now the original equation was y double prime minus 25y. So we have y double prime minus 25y, and that's equal to 0. So let's go ahead and plug in these things. I'm going to have all of this stuff in for y double prime. So there's my y double prime minus 25, and then my y, who is u e to the 5x. And we're going to set that equal to 0. Notice quickly that the 25 u e to the 5x's cancel out, and we get exactly what I was talking about. I'm going to rewrite this just a little bit. E to the 5x u double prime plus 10 e to the 5x u prime. That's equal to 0. Of course, as I was mentioning, divide both sides by e to the 5x, as we do with all of these problems. And we have u double prime plus 10 u prime equals 0. Next step, make the substitution. W equals u prime. So we get the equation w prime plus 10w equals 0. And our integrating factor then is e to the integral 10 dx equals e to the 10x. Multiply the whole equation by that, you get e to the 10x w prime plus 10 e to the 10x w equals 0. It's pretty clear that the left-hand side is the derivative of e to the 10x w. And so we know that e to the 10x w equals a constant, or if I want, w equals a constant times e to the negative 10x. So I've got that so far. Let me go ahead and replace w with the u prime. U prime equals c e to the negative 10x. U, of course, this is du over dx, so we can separate variables and do the integral of du equals the integral of c e to the negative 10x dx. So I'll get u equals negative c over 10 e to the negative 10x plus, I guess, another constant. Let's call it d. But the beauty here is I'm only looking for a solution. Like y1 was e to the 5x. I didn't need any constants with it because part of my answer has constants listed in it. So for example, I could rewrite this simply as c e to the negative 10x. I could let the c absorb the negative sign and the 10. And in fact, I don't even need the c. I could just, if I want to, use u equal to e to the negative 10x, because I'm just trying to find a y2. So you remember, y2 equals uy1. y2, my u I just found was e to the negative 10x, and my y1 was e to the 5x. So my y2 can equal e to the negative 5x. This says that my general solution will equal y equals c1 e to the 5x plus c2 e to the negative 5x. So you can see I don't have to worry about all those constants because they're absorbed inside of this c2. For the next example, I would like to do one that will utilize a great deal of patience, determine the general solution to x squared y double prime minus 3x y prime plus 5y equals 0, given that y1 equals x squared cosine of the natural logarithm of x is a solution. Here you can probably see, since we're going to be doing derivatives in that, these are going to get seriously ugly. And that's why I'm doing this example, to show you how far out these things can get, how bad the algebra can get. But you've got it, as long as you simplify along the way and keep things as efficient as possible, it shouldn't be too bad. The very first thing that I'm going to do with the equation is divide everything by x squared. So we'll do that first. Divide by x squared. What do we get? Y double prime minus 3 over x y prime plus 5 over x squared y is equal to 0. So there's the form we were talking about before. Now, as before also, we are going to let u equal y2 over y1, or easier, just set y2 equal to u y1. And so, like I said, having this y2 hanging around the whole time is annoying. Let me rewrite. I'll just use y equals u, and y1 was x squared times cosine of ln of x. Now I mentioned that there should be some sort of a symmetry to the answer, so I might expect x squared sine of ln of x to also be the other solution. So let's go ahead and plug all this stuff into this equation here. So the first thing I'm going to have to do is take the derivative of y, and then I'm going to have to take its second derivative. So let's go ahead and do that. Y prime. This is a product rule. What I'm going to do is I'll do u first, u prime, but I'll leave the rest of it alone, x squared cosine of the natural logarithm of x. Now I'll leave u alone, but this time I will take the derivative of x squared ln of x. Of course, that's also a product, so let me go ahead and do that part as a product. That's why I've started a parenthesis. X squared's derivative is 2x. Leave cosine of ln of x alone. And then leave the x squared alone and take the derivative of cosine of ln of x, and we'll get negative sine of ln of x. Chain rule says that you need to take the derivative of ln of x, and that's 1 over x. So I think I've completed these. Let me simplify as I go. Can't do much about 2x cosine of ln of x. But now I can cancel the x's a little bit, so I can get negative x sine of ln of x. Now, knowing that I have to take the next derivative, what I'm going to do is try to make life a little bit easy on myself. I'm going to say u prime x squared. There's not a lot I can do to make life easy, but I will do this one little thing. I'm going to factor an x out of these parentheses here. So I'll get a ux times 2 cosine of ln of x minus sine of ln of x. The reason why is the derivatives in here are not going to be product rules, so it'll be sort of self-contained. This will be a product rule here, this ux, but not such a bad one. All right, so let's go ahead and hit y double prime. I'm not sure how far over I want to go with this, how small I need to go, but this is not going to be pleasant. Y double prime. So we'll start here on this first piece. I'll get u double prime x squared cosine of ln of x, but then I'll get u prime times, now just like before, I have taken the derivative of x squared cosine of ln of x, and I got what's in these parentheses there, so I'm going to copy that. 2x cosine of ln of x minus x sine of ln of x. So that takes care of just this piece here. Now you'll see what I meant for the second part. Plus the derivative of ux will be u prime x plus ux prime. And then we're going to, of course, leave this part alone. 2 cosine of ln of x minus sine of ln of x. But then the product rule says that I've got to take the derivative of the stuff that was in parentheses. And so I will get negative 2 sine of ln of x times the derivative of ln of x. And the same thing will go on in the second piece. I'll get negative cosine of ln of x divided by x. Now, let's pause for a minute and simplify as much as I can. What I think I'm going to do is I'll stick with the first stuff that I have there. I have u double prime x squared cosine of ln of x. I'm going to, though, factor an x out of this part right here. Didn't mean to move the screen, but I'm going to factor an x out of this piece. So for that part, I'll get plus u prime x times 2 cosine of ln of x minus sine of ln of x. All right, also I'm going to realize that x prime is equal to 1. So it might not be a bad idea right now to change this, take it out. That's equal to 1. All right, let me do the u prime x and distribute it to this stuff. And I think I have it again. That's why I'm sort of writing it this way. U prime x times 2 cosine of ln of x minus sine of ln of x. And then I'm going to group all the u stuff together. Let me put plus u times that same stuff. And then this last piece, I'm going to multiply the x through and also factor out a minus sign. So that'll leave me with 2 sine of ln of x minus cosine of ln of x. All right, here I multiplied through by the u, but make a note of this. I had to fix this negative to a plus sign. So anyways, there is our y double prime. Let's see what I can simplify here, if anything. I'm going to get u double prime x squared cosine of ln of x. Here I see I have u prime of x, and I've got the same thing attached to it twice. I'm going to do plus 2u prime of x times 2 cosine of ln of x minus sine of ln of x. And then on these u's, I have 2 cosine of x minus a cosine of x. So that's going to give me cosine of x. Well, cosine of ln of x. And then on the portions with sine, I have negative u and then negative 2u. So negative 3 sine of ln of x. Alrighty. So there is my y double prime. Let's go back and see where the original equation was. There it is. Alright, let's go ahead and plug in y double prime. So I'll have to write all this stuff again. And I think I can just copy it. And then underneath of that, I think what I'm going to do is put my minus 3 over x is my y prime, and then plus 5 over x squared. Now y was equal to u times y1, which was x squared cosine of ln of x. And I'm going to do simplifying before anything else. For example, I'm going to take this x out with one of these and that one there. I'm going to take this x squared out. So we've got some simplifying that can happen. And then when I stack this up, I'm going to put my u prime x's underneath the u prime x's and whatnot. So let's go ahead and put all those there. This part, the u double prime, I mean the first line is fine. So we'll just copy and paste that one. The second line, I'm going to get negative 3u prime x cosine of ln of x. And then I'm going to get negative 3u times 2 cosine of ln of x minus sine of ln of x. And then I'm going to finish off with 5u cosine of ln of x. And let's simplify. This is where I need the u's to disappear on me. So we'll start with those. Here I have 1u cosine, and then I have negative 6u cosine. So there's negative 5 plus this 5 means I can wipe out all these cosines. That's positive looking. And then for the sines, I have negative 3u sine and positive 3u sine. So I can take the u's out all together. Here I can probably do a little simplifying. Here though, I'll have to attach a 4 to the cosine. And then we have 4u prime x cosine ln x. And then I have negative 2u prime sine x sine of ln of x. And then I have negative 3u prime x cosine of ln of x. Continuing. I have u double prime x squared cosine of ln of x plus u prime x cosine of ln of x minus 2u prime x sine of ln of x. And then one last thing I'm going to do is factor out the u prime. I think I'll take out an x also, but I'll take out the x in front of it all. And that'll leave me with cosine of ln of x minus 2 sine of ln of x, and then I'll put my u prime after that. Remember, all of this is set to equal 0. Now what I'm going to do next is I'm going to divide everything by x squared cosine ln of x. So that'll give me a nice u double prime to begin with. Plus, now I'll be able to take out 1x from here, but it will still leave me with a 1 over x. And then when I take the cosine Lx inside of here, I'm going to have 1 minus sine over cosine is tangent, so 2 tangent of ln of x u prime, and that's set equal to 0. So then next we're going to let w equal u prime, so the equation becomes w prime plus 1 over x times 1 minus 2 tangent of ln of x or w. That'll equal 0. Now you can see the integrating factor is this stuff that's in front of the w. So I'll make myself a big E and a big integral to handle it all. I'll have 1 over x minus 2 tangent of ln of x over x, and all of that stuff dx. Of course, the 1 over x is easy. I'll get e to the ln of x. The second part, I'll have to step it through, but I don't want to do a lot of details on it. If you allow, say, a letter v to equal ln of x, then dv will be 1 over x. So this is like negative 2 tangent of v. Antiderivative of tangent is negative natural log of cosine. So this is 2 ln of cosine of ln of x. I'll break this up. E to the ln of x times e. What I'm going to do is take this 2 and put it on top of the cosine. So I'll get ln of cosine squared of ln of x. And of course, the e's and the ln's cancel. I'll get x times cosine squared ln of x. So that's what I'll multiply everything by. So I'll get x cosine squared of ln of x w prime plus x cosine squared of ln of x times 1 over x times 1 minus 2 tangent of ln of x times w, and that equals 0. Of course, I can cancel the x's here. Now, I do want to see if this actually does work out. So, even though I know that this comes out to be d of x cosine squared of ln of x times w. But I just want to make sure. Think about taking the derivative of just this part here. The derivative of x is equal to 1, and that did go away. And you would be left with just cosine squared of ln of x. In fact, if you multiply it through, you have cosine squared of ln of x in that spot. Now, then for the second piece, though, when I take the derivative of cosine squared, I'll have 2 cosine of ln of x times negative sine of ln of x over x. That'll cancel, so let's think about that again. Negative 2 cosine sine. So if you take cosine squared into tangent, one cosine will cancel and you'll get negative 2 cosine sine, like I said. Of course, this means that x cosine squared of ln of x, w, equals some sort of a constant. Well, we're just finding an answer, a y2. So none of these constants matter, but they'll help out as I do this one part of it. W equals secant squared of ln of x. That's 1 over cosine, but then I'll have over x. And I'm dropping the c right now. W is equal to u prime, so I have u prime equals secant squared of ln of x over x d. No dx yet. But quick enough, u will equal the integral secant squared of ln of x over x dx. And that's pretty easy to integrate, actually. If you think of v as being ln of x, then 1 over x dx is the dv portion of it. The antiderivative of secant squared is tangent. So this equals tangent of ln of x plus another constant. I'll call it k. It really doesn't matter. We can drop it off. I'm mentioning it because normally you would have it there. Now we're ready for my y2. My y2 equals u y1. Well, here's my u. So we're going to have tangent of ln of x times x squared cosine of ln of x. And you probably could have seen this coming because the cosine here is going to cancel with the cosine in the denominator of that, and we'll end up with x squared sine of ln of x. And as you might have imagined, this gives the general solution. And that'll be y equals c1 x squared cosine of ln of x plus c2 x squared sine of ln of x. As if this horse isn't beaten to death enough, I'm going to do one last example, but this time I'm going to do a different style of equation. Here, let's solve y double prime minus 4y prime plus 3y equals x. That's something different right there. Given that y1 equals e to the x is a solution to y double prime minus 4y prime plus 3y equals 0. So here's the deal. I'm giving you a solution to the homogeneous version of the equation, but I want you to solve for the non-homogeneous equation that you're given. So here's the non-homogeneous equation. And down here is the homogeneous. So first thing I'm going to do is find a second answer to the homogeneous version. That will give me a complete set for those. Let's do that first. So first, solve the homogeneous equation. All right. With that, then I know that y1 equals e to the x is a solution. So like I did before, we'll let u y1 will equal y, and I'll need to take a first and second derivative. I've done it a few times, but it doesn't hurt to do it again, I guess. Y prime equals u prime y1 plus u y1 prime. Y double prime equals u double prime y1 plus 2u prime y1 prime plus u y1 double prime. And we know that e to the x is what I'm going to be plugging in for y1. Well, these are easy then, isn't it? Y equals u e to the x. Y prime will equal u prime e to the x plus u e to the x. And then y double prime will equal u prime prime e to the x plus u prime e to the x plus u prime e to the x plus u e to the x. I should have taken my own advice here. This equals u double prime e to the x plus 2u prime e to the x plus u e to the x. Plug these all into there, and hopefully you can see that e to the x can absolutely be factored out of everything. So let's go ahead and throw it in. Y double prime minus 4y prime plus 3y supposedly equals 0. I'm going to take an e to the x out of everything, so e to the x. So what will be left for my y double prime? I'll have u double prime plus 2u prime plus u. And then I'll have minus 4e to the x. And then what was y prime? U prime plus u. And then I had plus 3 e to the x, and that would be times u. So I'll factor out an e to the x out of all this stuff. Let's use brackets this time. U double prime plus 2u prime plus u minus 4u prime minus 4u plus 3u. What we need is for the u's to go away, so I got u minus 4u is negative 3u plus the 3u, they do go away. And my u primes, I have negative 2u primes, so I got e to the x u double prime minus 2u prime equals 0. Obviously, divide through by e to the x, and we're left with solving u double prime minus 2u prime equals 0. Once again, w equals u prime. So we're solving the equation w prime minus 2w equals 0. The integrating factor, e to the negative integral of 2 dx equals e to the negative 2x. And so I multiply the equation by that. I'll get e to the negative 2x w prime minus 2e to the negative 2x w equals 0. The left side is d of e to the negative 2x w. Set that equal to 0. That means e to the negative 2x w will equal a constant. From this we get w equals ce to the 2x. The constant is not important at all. Replace w with u prime equals ce to the 2x. So u is the integral of that, so it's c over 2e to the 2x. Or I really just need u equal e to the 2x. So my y2 will equal u y1 will equal e to the 2x times e to the x equals e to the 3x. So if you recall, our equation was to solve y double prime minus 4y prime plus 3y equals x. There will be two components to our answer. Our solution will be of the form y equals y sub p plus y sub c. Now the y sub c we found. Y sub c equals c1, and our y1 was e to the x, plus c2 e to the 3x. Our complementary solution, if you will. Y sub p is a particular solution. And can be any solution to y double prime minus 4y prime plus 3y equals x. So we have to find any kind of possible solution that just simply makes this equation work. I throw it in, and instead of 0, I get x. So I'll need that for y sub p. So it's a guessing game. So let's do some trial and error. When you think about this, all I need to do is come up with x somehow. If y sub p was equal to x, look what would happen to it. If y sub p equaled x, y double prime would be 0. But 4y prime, the negative 4y prime would be negative 4x. Or negative 4, sorry, y prime would equal 1. I would have negative 4 plus 3x, and that doesn't quite work. Now, if you try to do anything like, obviously I can't have just a number be a solution here, because all the derivatives would be 0, but then 3y would turn out to be a number, and that wouldn't be good at all. So I think I can do something like this. Let's try a solution like this. Y sub p equals ax plus b. Some sort of a function like this. Check out why I'm thinking this. If I take its second derivative, that will zero out. That's always a bonus. Now, if I take the first derivative, I'll have negative 4 times a. But then if I take no derivative at all, I'll have 3ax plus 3b. Now I'll have a negative 4a in this spot, which will be a number. In this spot here, because I have an ax plus b, I'll have an x term, 3ax plus 3b. That 3b will have a chance to offset the negative 4. That way, I have a chance of zeroing out the constant parts and leaving me with just x. Check it out. Let's go ahead and do these things. If I plug it in, I'll have yp double prime minus 4y sub p prime plus 3y sub p. Let's go ahead and plug these things in. All right, so yp double prime, as I mentioned, was 0 minus 4. Now y sub p prime will simply be the number a. And then plus 3y sub p will be 3 times ax plus b. And this needs to turn out to equal just x. Now watch what I do. I'm going to have negative 4a plus 3ax plus 3b equals x. I'm going to go one step further and see if you can follow me here. I'm going to rearrange my left side into the following. 3a times x plus 3b minus 4a. That's the left side. On the right side, I'm going to rewrite it as 1 times x plus 0. The reason why I did that is because I'm going to line up the coefficients. In front of the x, I have a 1 on the right side. On the left side, in front of the x, I have 3a. So I am allowed to make the equation 3a equals 1. In other words, a is equal to 1/3. On the other hand, now that I know that, the constant part up here, the 3b minus 4a, is equal to 0. So I have 3b minus, now a is equal to 1/3. So it's 4 times 1/3 equals 0. And now all I have to do is solve this equation for b. First thing I would do is multiply through by 3 and get 9b minus 4 equals 0, or b equals 4/9. And so what I can use for my particular solution then, y sub p equals 1/3 x plus 4/9. So my solution, by the way, you may want to just throw it in to make sure it works. Let's actually see if it does. Y double prime on that will be 0, like we said. Y prime will just be 1/3, so I'll have a negative 4/3. And then let's see what happens when I do 3 times the whole thing. So I'll have negative 4/3, remember that, plus 3 times all of this. 3 times the 1/3 of x will give me the x like I want. 3 times 4/9 will give me positive 4/3. And the negative 4/3 will have canceled out. So my solution, remember, looks like this. Y equals y sub p plus y sub c. So it equals 1/3 x plus 4/9 plus c1 e to the x plus c2 e to the 3x.